For the first speaker, Yen Beer from Google, he will be talking about got root, compromising OSX. All right, so can we please give a warm round of applause for Yen Beer.
Originally, this talk was just going to be about OSX. Oh, maybe that's better. About OSX, but iOS is much more exciting. So all the bugs that I'm going to talk about, as well as being local privilege escalations on OSX, are also local privilege escalations on your iPhone. So who am I? I'm a vulnerability researcher. I currently work for Project Zero at Google. I used to be part of the Chrome security team. I enjoy browser bugs and sandboxing layers. And over the years, I found a bunch of bugs and written a bunch of exploits for things like Chrome, Safari, Firefox, Flash, OSX, and iOS. In particular, this talk is going to be about the last two of those, and specifically about one small part of the sandbox attack surface, kernel attack surface on OSX and iOS, called Iokit. So for those of you who don't have a background in Apple development, we're going to talk about what Iokit actually is and why Apple developed this thing. We're going to talk about how it works, and of course the best way to talk about and to understand how things really work is to break them. So we're going to deep dive hopefully into 3 different bugs, which are going to show you 3 different types of attack surface that you have on OSX and iOS. So what is Iokit? So the main thing to understand about Iokit is that it is the premier source of Apple kernel bugs. What it in fact is the OSX and iOS kernel device driver development framework. So I was going to say uniquely it's written in C++, but actually Windows 8 now also has a C++ driver development framework. So the Apple documentation for Iokit will tell you that actually it's just a small subset of C++. But as we're going to see, there are a few features of C++ that are left out, but there are some kind of exciting and interesting extra ones that are added in. Like with so much Apple code, I would define it as sort of open source. Some bits are open source, some bits are not. It's completely unclear why Apple decided to open source some parts and don't open source other bits. OpenSource.apple.com is your unreliable friend. Sometimes you will find that the things you want are there, sometimes they are not. And for everything that isn't, if you check out system library extensions on your MacBook, you will find where all of the Iokit kernel extensions live. Quite nicely, Apple don't strip the symbols from device drive, or from most of the device drivers on OS X. This is quite different on iOS, where things are much harder. So what actually is Iokit and what does it provide? So the fundamental thing to understand about Iokit, and the reason that it is written in the way it is that it's trying to encourage code reuse through C++ inheritance. What that really means is that if, for example, you are developing, say, a new mouse or a new HID device, what you will do is take an existing HID device driver and simply subclass it. You use C++ inheritance to take existing code and literally override the methods that provide the specific functionality for your device. So some of these base classes or families of base classes are open source. So for example, IOHID family. And for those of you who still read full disclosure, there was a OSX local privilege escalation Ode posted on full disclosure 2 days ago with a bug in this bit of open source code. There are some other closed source families, for example, IOAccelerator. And IOAccelerator is the family that provides all of the base classes if you want to develop GPU drivers. So as well as providing these base classes, what Iokit also gives you is a complete C++ standard library runtime. This is called libkern, and it gives you all the things that you would expect from a C++ standard library, so memory allocation functions, and also implementations of about 15 standard types, so things like arrays, or in this case OS array, OS string, OS set, OS dictionary, and the list goes on. A kind of interesting quirk of the way that you will interact with Iokit, and we'll get to this later when we see some examples, is that an awful lot of the APIs are XML based. That means literally you talk to your kernel by sending it XML. So there's this thing called OS unserialized XML, which is a kernel mode XML parser. It's actually not as scary as it sounds. It's quite small. And really what it is more like a compatibility layer between user space. So if you have ever developed any user space code on iOS or OSX, you'll be familiar with Core Foundation, which is their kind of Apple C runtime, sort of, that provides a bunch of standard types. Things like Core Foundation array, Core Foundation string, Core Foundation set. So you can see that there are analogies in user space for all of these OS array, OS string data types. And so what this XML layer really does is provide a compatibility layer, or provide compatibility between user space and kernel space. If you have a kernel device driver that's expecting a dictionary of arrays of sets of strings, you create this in user space, create it in user space, serialize it as XML, and then on kernel in the kernel, deserialize it, pass it to your device driver method. So how on OSX do we actually talk to these Iokit device drivers? So there are three main interfaces on OSX that we use to talk to the kernel. The first is very familiar if you've ever done any kernel mode stuff, or if you've really done any user space programming on any other platform. So it has a full Bsd kernel interface, which you just access via the standard syscall instruction on 64-bit. So it's about 300 syscalls, and every new release of OSX, they add 5 or 10 new weird ones. There is a second set of syscalls, again accessed via the same syscall instruction, but just with a bit set in the upper 8 bits of the syscall number. And these are an interface to something which you might not have come across if you've only looked at Linux or Windows. OSX has this notion of having a second microkernel interface as well. So as well as having BSD, there is also this thing called Mach, which is living in there. So from our point of view, the Mach microkernel interface only really provides us with one thing, which is this really nice low overhead IPC mechanism. And this is used to allow us to talk to a whole bunch of Mach kernel services. So if you're familiar with the idea of how microkernels are supposed to work, the idea is that your kernel is very small and only has really the ability to provide an IPC foundation between user space processes. On OSX, it doesn't really work like this. It has the framework for doing this, but actually all of these Mach kernel services live in the kernel. And the way that we talk to them is, rather than them all having dedicated syscalls, they're all kind of proxied via this Mach message syscall, or in Mach parlance, a syscall is called a trap. So the interfaces for all of these services are defined in these interface definition files. And this is where you can find them in the XNU source code, which you can get from opensource.apple.com. And the way these work is that when you actually compile your kernel, it takes all of these interface definitions and runs this MIG, Mach interface generator tool, to generate serialization and deserialization code, as well as just C header files that you can include. So this is an example of Mach interface definition, so routine IO service, get matching service. So this is not a syscall, but in effect, the reality is that it actually is a syscall. It's simply proxied via a Mach message. So just to show you in a diagrammatic way how that works, we have user space on the left and kernel space on the right. So when we built our kernel, what we did was take all those interface definition files and auto-generated a bunch of C code, some of which lives in user space, some of which lives in kernel space. When we want to call this kernel space code, we call into the user space code with our arguments. It serializes them into a buffer, makes the Mach message trap, which then sends that message, literally copies that message, in fact, into kernel space, takes the ID field of the message looks it up. This function IPC k object server looks it up in a hash table, finds the right deserialization code to call, and calls it. So let's get back to what an Iokit driver actually looks like. Where can we find bugs and how do we talk to them? So as I said, the fundamental paradigm in Iokit is C++ inheritance. You take the existing code, which does almost what you want, and you inherit from it, subclass it, to add your specific bits. So I've said here that the two main kind of fundamental classes that you're going to be interested in are IO service and IO user client. So it's kind of a bit wishy-washy to say you subclass IO service to provide driver functionality. Your driver would have to be very simple to only subclass just IO service. Generally, you'll have a whole bunch of helper classes as well. But the thing that we're most interested in today are subclasses of IO user client. So IO user client provides the framework, the building blocks to provide interfaces for your code to talk to user space. So there are three main ways that Iokit drivers and user space can interact. We're going to look at three kernel bugs in each of these interfaces, so one kernel bug in each one. And again, all of these, the most recent one was patched in iOS 2 weeks ago. So the first type of interface that we have are things called external methods. If you're familiar with Linux or Windows, these are most similar to ioctls, IO controls. Essentially, your driver provides numbered methods, and from user space, you can invoke these methods with controlled arguments. And the second user space interface is via shared memory. What you can do is simply ask your driver, make me a heap allocation on the kernel. It's not quite that simple, but the driver will typically make a heap allocation and share it with user space, and then they're free to do kind of whatever they want. And we'll see some funny bugs there. The third type of interface is via these things called registry properties. And basically, drivers can expose a set of key value pairs, and some of them are configurable. So we'll have a look at those as well. So the first type, external methods. From user space, we call this wrapper function IOConnect call method. As we saw before, this is really just a wrapper around one of these MIG auto-generated serialization methods. In particular, this is a wrapper around IOConnect method. And this allows us to pass unstructured data to IO user client external methods. So if you're looking at iOS or OSX drivers and you want to find where this data will be passed to the user client, you're looking for one of these three methods, the external method, get targeted method for index, or get external method for index. So the example bug that we're going to show that is reached via an external method is in one of these extra bits of C, or an extra bit of functionality that Apple have added to C++, which I mentioned, and something that might sound kind of strange. So I hope that the phrase C++ reflection kind of jumps out at you. If anyone in the audience, and I'm sure most of you have ever read any write-ups of Java exploits or Java bugs, almost every single one of them is a bug in the way it does reflection, or at least uses reflection. So in Iokit, when you define any new type, there are a set of macros that you have to use. These macros are there to tell this Iokit subsystem called OS metaclass how it's able to tell OS metaclass, firstly, what's your class called, and secondly, how can OS metaclass call the constructor of your type. Code can then call OS metaclass alloc class with name to instantiate any Iokit object just with a string. So this is a very kind of tempting and interesting API to look at. But surely there is no way that this is exposed to untrusted input. But unfortunately, as is true with so much of security, if you have a dangerous API, there will be some developer somewhere that will find a way to pass untrusted input to that API. So this is our case study. So IO surface is a simple wrapper around a shared memory buffer. For example, if you are developing a web browser and you want to separate different parts of your web browser and have, for example, a renderer which renders the actual content of the web page to a buffer and then it's displayed, you'll use on OSX or iOS an IO surface. So IO surface root user client is the user client, which I mentioned earlier, that lets us interact with these IO surfaces. And importantly, it's reachable in the most interesting sandboxes. So on iOS, that's Mobile Safari. Excuse me. Mobile Safari, which is the place that all your iPhone ads, which are served over HTTP, are rendered. And also the Chrome renderer on OSX, as well as the Safari renderer process, also on OSX. So IO surface root user client might sound familiar to those of you who followed the iOS jailbreaking scene. So this was involved in Comex's Jailbreak Me 2 iOS jailbreak for, I think, iOS 4. So here's example of calling external method 0, which is create surface. So literally the API, the data that you pass to the kernel is this XML string. So you can see that it's passing IO surface bytes per element 4, IO surface width 40. So you can kind of maybe guess at what Comex's bug was. There was a simple integer overflow when it tried to calculate the size of the surface to allocate. It would take the width, the height, multiply them, and the buffer would be too small. The code, when you look at it on the surface, doesn't appear to actually do that much very interesting. And if you just set a breakpoint there and dump the XML which you see in the kernel before it's been deserialized, back into an object, you'll see that actually it's always this kind of same thing, and it's nothing particularly interesting. But if you actually open up that, take a look at that method in IDA, you see that there's actually code there that is looking for an extra key, IO surface class. And if we specify this extra key, the value will be passed directly into that C++ reflection API, i.e. from user space, from actually from one of the most sandboxed processes on your iPhone, you can reach this reflection API with a controlled string. So there's not necessarily any problem with that, but it's certainly a very interesting area, a very interesting piece of code to look at. So let's look a lot more closely at what it actually does. So the first kind of slightly weird thing is that the way that you can check, or the way that it checks whether the type of the object it just instantiated was valid, uses this safe meta cast method. And safe meta cast only operates on objects, which means the code first has to actually allocate the new object and then check if it was safe, if it was a safe type. That's kind of okay, there's no actual bug there, except, well, if you actually take a look at the disassembled code and work out what they must have done, what they've actually done is explicitly cast the return value of that call to the reflection API to an IO surface pointer. And remember, we've been able to specify any kernel C++, any Iokit kernel C++ cast we want. So that's kind of okay, except you have to be really careful how you use that IO surface pointer. And what they in fact do is if the inheritance check fails, the code actually calls an IO surface virtual method to destroy it. And that's not okay. So this is the bug, and it's kind of subtle. And I definitely had looked at this code probably 2 or 3 times before I finally realized, hang about, there's a really awful bug here. So R12, this is so Intel 64-bit assembly. So R12 is the return value from the call to the reflection API, where we can allocate a class with a name. It's then calling the virtual method. You can see it reading the vtable pointer and calling the virtual method at offset hex 120 in the vtable. To most people, this would not stand out as a bug. And in fact, only when you've stared for long enough in IDA at various Iokit kernel methods do you realize that actually hex 120 is outside of the range of it's outside of the size of the vtable of the base class of all Iokit objects, which means this is actually calling a virtual method on IO surface or one of its derived children. What that means is that we can reliably call the function at offset hex 120 in absolutely any Iokit object vtable. So the thing that makes this kind of tricky is you don't control the arguments. And so the kind of bug you're looking for here is one where the function is expecting to be called, for example, with many arguments, and this calling convention really only passes the this pointer. So we don't know what those arguments will be, but we kind of know what they'll look like. On OSX, this is actually super trivial to exploit for Bsd, and iOS is left for an exercise for the reader. So the second communication mechanism that we're going to look at is shared memory. So again, we have this user space wrapper function, IOConnect map memory, which wraps this IOConnect map memory MIG method, so one of these auto-generated serialization and deserialization methods. And what this really does is ask the user client code to give it some shared memory. So defined IO user clients which implement this, you want to look for their client memory for type, i.e. the user clients which support this method will simply override this function and provide their own implementation. And pretty much every single user client which I've found thus far has managed to implement this completely wrong. So the interesting first example for this is IO data queue. So this is a utility class used by lots of methods which override the client memory for type method. And the idea of IO data queue is to be an abstraction that allows kernel space and user space to share a queue. The idea being that, for example, the kernel has a series of data objects, like events, that it wants to send to user space in a very low overhead manner. So what will happen is that they will set up this queuing structure in shared memory. The kernel will enqueue things into the queue, and user space code will dequeue stuff. So you can imagine that actually to implement something like that properly is going to require quite a lot of complicated stuff. For example, you're going to want to make sure that you can correctly lock the data buffer so that user space can't interfere with any of the information in there while the kernel is enqueuing stuff. So there are a bunch of IO user clients which used various subclasses of IO data queue. So you would think that implementing something like this was actually pretty complicated. This is the way that it worked in the iOS and OSX kernel. And by the way, I think this was used in the Pangu jailbreak. Maybe Stefan Esser will talk a bit about this later. And I reported this about the same time, I think like 2 days before they released their jailbreak. So the way that IO data queue sets up this shared memory structure is simply to make a kernel allocation, share it with user space, and have these 3 integer values at the start of the shared memory. So the queue size, the queue head index, and the queue tail index. And then, as you can see here, this is just followed by the inline queue data. Hopefully, this stands out as being very wrong, because every single one of these values was completely trusted by the kernel. So firstly, the queue size field, when you when you close the shared memory mapping, the IO user client would, the IO data queue method would simply take that queue size value and pass it directly to kmem3, which is a kind of low-level kernel memory allocation function, which takes a pointer to memory to free and the size in pages to free. So by changing this queue size value, you could tell the kernel, take that shared memory allocation, free it, and also free the page after it. Not only that, whilst the enqueuing side on the kernel, in the kernel, did have some bounds checking, the 2 values that it used to check the bounds were the queue size and the tail index, i.e. those two values which are both in shared memory. So this is absolutely trivial kernel heap memory corruption. So the third interface for talking to Iokit user clients are these Iokit registry properties. So again, the way that you interact with it is via this wrapper function with the rather long name of IO registry entry set core foundation property. So this is, like all the others, really just a wrapper around this IO registry entry set properties MIG method. It's yet another XML-based API, but unlike the other two, this thing is generally forbidden in most sandboxes. So again, if you're looking for Iokit kernel drivers which implement configurable registry entries, i.e. registry entries that you can manipulate, look for code which is overriding the set properties method. So there is actually this convenient command line tool on OSX called IOReg, which lets you interrogate the Iokit registry, and you can just dump all of the values which the Iokit registry knows about. So here's an example of asking the Iokit registry to tell us about the IOHID keyboard class. And you can see it's just dumping us back a set of key value pairs, most of which are kind of uninteresting. Excuse me, apart from that last one, HID key mapping, which looks like some kind of structured data that's clearly not just an ASCII string or something uninteresting like that. So what we want to know is this configurable, i.e. if we call the set properties method of IOHID keyboard, can we configure this data, and what is it actually used for? So luckily, IOHID family, as I mentioned earlier, is one of the open source Iokit families, which means that we can quite easily just grep for this HID key mapping key. And if we do that, we reach this bit of code here. So you can see in the first line that this is expecting us to have sent it a dictionary, so an XML dictionary, with the key HID key mapping, and the value being a data buffer from OS data. And this data is going to be passed straight into IOHI keyboard mapper, passing the map function. So this is just a pointer to completely controlled data. So before we look at what the actual implementation of that function is, it's important to remember that an awful lot of the Iokit code is really, really old. So this function is from 1992. So the Iokit code base is derived from DriverKit, which was, or it's derived from Next. Next Step, which was the operating system developed Next that Apple bought in the mid-90s. And as you expect from really old code, it's got some awesome old-school C code with old-school C bugs. Remember, this was reachable on your iPhone. So the next num function is reading shorts from your controlled data buffer. So you can see here on the first line, we're just reading a short into num sequences. Then there's some bounds checking, except this is kind of checking the wrong way. This is checking that the num sequences value is not less than or equal to an upper bound. If it's less than max sequence number, then we fail. There is no upper bounds check. And if we then look at how num sequences is used, it's simply used as a loop counter to iterate through and write to this sequence defs function there. That sequence defs, write to that sequence defs array. And that sequence defs array is just a fixed sized buffer on the heap. This is super, super trivial to exploit, and you can check out the Project Zero bug tracker where there's a working exploit for this bug. So the conclusion is really about OSX and iOS kernel is that the code, there is absolutely nothing special about iOS kernel code. It's simply about knowing where to look. This was absolutely just the tip of the iceberg in terms of trivial kernel vulnerabilities. None of these were at all complicated, and they've mostly been there trivially exploitable for the entire lifetime of OSX and iOS. In fact, some of those APIs, by simply calling them with any invalid data, not invalid data trying to hit a particular bug, but simply any invalid data, was enough to trigger exploitable kernel bugs. So there were quite clearly not enough people looking at OSX security in the public. So yeah, that's the end of my talk. And please, if you're interested in finding out more about any of these bugs, or any of the other work that we've been doing, check out the Project Zero bug tracker, where there are detailed write-ups for all of these bugs and a bunch more. Any questions? I don't know if there's a microphone.
Hi there, just a quick question. So the interface for XML passing is through the message, right? The syscall is by registers as usual?
Yes, so the syscall, the Mach trap syscall, is just a regular syscall. And the XML is contained in this Mach message buffer, a pointer to which is in one of the registers. When you make the syscall, that then gets copied into kernel space.
Okay, but let's say I go through the normal BSD or Mac kernel syscall, there's no XML.
No.
Okay, thank you.
What's next?
Good question.
I'd say more recently I've been looking, this talk was only about the kernel side sandbox attack surface. There's actually a much larger sandbox attack surface available in user space. There are something like 50 daemons that run as root. That's a rough estimate. And the code is equally bad.
Okay, Yan, thank you very much. Thank you. A round of applause for him.